Okay, um, welcome everybody to the fifth learning lab. This is the fifth lab that we're going to be presenting by the Cruz Data Science Initiative. And we are in the machine learning block. So I'm going to start sharing my screen and I'm going to start to show what we are doing. So for today's presentation, we are going to be using machine learning as to classify lithology from wireline logs. It's also called Facies classification. Let me just turn off my video so you're gonna get the full screen better. So it's gonna be presented by me and Daniel Tread. So just as a agenda for today, I'm gonna give a small explanation. What is the Cruz Data Science Initiative? And then we are gonna give an idea, what is a data science project? Data science project is not only the machine learning part. So for this talk today, we're going to be presenting all the steps of a data science project that goes from loading the data, doing some cleaning, data analysis, feature engineering, and modeling by the end. So we're going to talk about the Facies classification and from where we got the data set. That's a competition from the SCG 2016. And they're going to give a small explanation how to use deep learning for regression, the model that we're using for using regression. For this one, we are just, well, sorry, there is a problem here. Sorry. It was my Zoom saying that there are people waiting. I apologize for that. So we have a regression for deep learning, and then also we're going to using gradient boosting from the package XGBoosting for the classification of the faces. So the hosts of today, it's me. I'm Marcelo Guarida. I'm a data scientist, and I'm with a PhD in geophysics. And nowadays I'm the head of the Cruz Data Science Initiative. And my co-host is Daniel Tread, that is going to be here giving any support. He's associate professor and chair of exploration geophysics at the University of Calgary. So just as I start, this is how we do our data science. This is the Cruz Data Science Initiative. Cruz is famous for doing some seismic research for more than 30 years. And now you're starting this data science initiative where we are going to be focused on projects in data science based in geoscience, and they're going to be doing academic and industry projects related. We also provide some training in programming that could be initial training for R, Python, and MATLAB, as well more specific training for data science projects that include machine learning and everything with the focus for geoscience data set, and also how to create apps using, for example, the Shiny and other packages that you can create. And one of the products that you have is this learning lab that you're presenting every 2 weeks that are open to everybody. You can watch and you can access as well the information from the previous labs. If you go to the Cruz website, to the research links and data science. So that is going to be this website in here. If you go to the Cruz website, you have the research links tab, data science, and you can have all the information from the previous labs, and also you can download the files that you used for the lab, all the coding in R and or Python. So, okay, so let's start talking about the project. So this is a data science project. How we have, it goes from since the start of the idea, where we have to access data, raw data. We need to have an idea or project, and we have raw data. The next step that we have to do in this workflow is to process the data. That includes data cleaning, but more than that, not only data cleaning. It includes as well data analysis, data imputation, feature engineering, and many other things that you're going to be doing. So we're going to be in these 2 steps in here that you're going to spend approximately 80% of your time, basically. and just a little bit time in your modeling step that you're doing the machine learning. So that's why it's really important for you to understand your data that you're working with, because you're going to spend a lot of time before doing the modeling. And there are also parts of the deployment and the monitoring. The deployment is to create a product that you can deliver to your client. In the previous labs, we showed how to create Shiny apps to deliver to your client. That can be a external or internal client or any other organization. And you keep doing rotations in this. So we can keep improving when you have new data, we can have new ideas for data processing, new models, and doing for that. And for this project, you're going to be using R in RStudio, and it's very useful for you to know the library Tidyverse for all the data processing, to access the data, and also for data processing. This is a very powerful package in R where you can do a lot of stuff. So for the project that you're going to be talking today, that's the Facies classification. For people that don't know what is a well log, basically when you have a well for any purpose, that can be for oil and gas, mining, or anything, you can pass through this well, an apparatus that make a lot of measures in the rocks around it. So you have a truck that sends the cable down, and let's say every 15 centimeters or any sampling rate that you want to have, the machine stops and makes measurements of the rocks around. So this is an example for the gamma ray apparatus that's being passing through. And this is what we have. By the depth that is going down, the measurement of gamma ray that we had. And the goal of our project today is to use a lot of the bunch of those provided well logs that we have, like gamma ray, induction log, and so on, to try, and the core analysis, when they actually do some core analysis of the rock by depth, try to use all those informations to predict what should be the core analysis. So we're going to show you how to get to these results that are very reasonable results that you're getting in here. So the data set, it comes from, I'm going to show you from this GitHub. You can access it. This is a 2016 machine learning contest from the SCG. So you can have access to all the data set and also to several notebooks of the participants. And you can have a look, you see their scores, and you can have an idea what they did in here. So most of people did in R, a few in Python, sorry, and a few in R, one in Lua. So you can access, for example, if you access the champion notebook, you can have an idea what was done in here. So going back to the presentation, for the now, one of the things that you're going to be using here, one of the models we're going to show you clearly is the deep learning. That's the neural networks you're going to be using for data imputation, for the missing data. And the neural networks has this draw. So this is the machine learning area. So we have the machine learning. And you have the inputting data. That would be your features that you have, in this case, the well logs. You're going to create some combination of them by multiplying each one of them and summing each one of those hidden layers and these hidden sessions in here, each one of those perceptions. You're going to multiply by this one weight here, and you're going to have an activation function. So you're going to be creating a very complex equation that you're going for the output and try to do classification or regression. When you have just one layer, hidden layer, it's called a neural network. So everything that has two or more hidden layers, it's called deep learning. So you're going to be passing through all these weights, and that's what you're going to be training. Those weights, we have to calculate what are those weights that are given to our output. And for these, you're going to be using the libraries Tide Models, Parsnip, and Keras in R. And also the net. Yeah. And for the classification, you're going to be using XG boosting for the gradient boosting. So the idea of the XG boosting, it's a ensemble classifier that combines several decision trees. And a decision tree is something like that. You have the first step in here. You're going to decide, for example, if you have data to be approved loan for someone. So you have the first one here is the credit history or credit check. Is it good? So goes to decide. If it's bad, go decide. So, and then you're gonna look here, oh, what's the income? Good, go decide. And then you're gonna have this decision. If it's bad, this decision. And here you can have another feature that starts to be divided. And it's called a decision tree because of the similarity that it has to a tree, right? And the ensemble classifiers that you can have is when you have several trees, because a decision tree alone by itself, usually it's a very weak classifier. So you can have the ensemble organized randomly, where you create random trees and combine them in the end by a voting system. And this methodology is called the random forest. Or you can have another way to have is to create one tree after the other. So you create a decision tree, see the results that you had, calculate the errors, and then you train a new tree based on the errors, and you keep doing that one after the other. So this is called the gradient boosting, and that's the methodology that you're going to be using in here for the classification. So that's a small explanation that I'd like to give about what you're going to be doing today. So let's go for the code. So for the code, you're going to be using R. This is my R section. And here, that you're going to be provided later this week, you're going to give in the data. So this data that was provided in there in the GitHub web page is these Facies vectors. This is a CSV. We can even open the CSV if you want in here. Just take a look in it. How is it? So we have the first row to be the name of each column, and we have all the information. So we're going to have the faces, the formation type, the well name, and so on. Those are going to be all the informations that you're going to be using. So we have the well logs, and you also have two indicators that has this marine and non-marine indicator and a relative position. And also what you're going to have here are the project. We have these utils.r. Those are some help functions that also is going to be provided. So it's going to be here. You can check here. Each one of those names in here is a function that are going to be for our help. I'm not going to go through those functions, but you're going to have access to it. And you have the markdown. That's our markdown file that if you need, you're going to have this HTML file as well that you can even open your web browser if you don't want to run. If you just want to check this, that's the type of report that you can deliver to a type of a report that can deliver to a client, for example, an HTML report, and you can even include some interactive figures and as well. So let's go back to the R. So let's start. So what you're going to be doing here, I'm just setting some chunks in here to have always warning and messages to be false. So when you're going to be knitting, it's not going to show any warning in any message. The figures, they're going to be centered from the HTML file, and the resolution is going to have a quite good resolution. So if you want to run this chunk in here, this R chunk, you can press Ctrl-Shift-Enter, or you can go to this arrow in here. So we run this chunk. So the first thing that you're going to need is to load the libraries that that's going to be required for us. And let me just restart my section in here and clean all the outputs. So yep, so I'm going to just rerun this chunk. And those are the libraries that you're going to be using. For the core libraries, the ones that you're going to be using more important way are the tidyverse, that's for the data preparation or data wrangling, the reshape, because I'm going to need to do some reshaping of the data as well. And this package, reticulate, it's a package where we can run Python from inside R. So I'm going to show you just an example and how to do a pair plots we using Seaborn inside R from the Seaborn packaging in Python. So I'm going to load. If I just want to run these 3 rows in here, I just select them and do Control Enter. So now I loaded these libraries. And the next one is for the modeling. For the modeling, I'm going to be using the tidy models. The tidy model, it's a very powerful package that combines several other machine learning packages in R, and it's very simple to use. So I'm going to show how to use soon. So both the Keras and the XGBoosting, we're going to be using from the tidy models. And to compute our metrics, you're going to using the library ML metrics. And for the plots that you're going to be using, you're going to be using the ggplot2. That's the most common, the most used visualization package in R. And this ggAly, it's for another way to do pair plots, but this is in R. So I'm just going to show you both examples in Seaborn and in R. And here I'm just going to be sourcing my helping functions. So I'm going to be loading in here. So in this part, I'm just loading the data. So it's in this folder 00 data and named the faces underscore vector.csv. Now I'm loading to the data, and then you can have a quick look to the data. So we are creating here the 10 first rows. So we have the faces, the formation, the well name, and so on. So all those names of the columns that you're going to be using for our research. And we are going to be showing in here. I'm going to show this table in the HTML file that we opened. So it's going to be easier to visualize. Oops, I'm sorry. I have to open again because I closed it. So a small explanation is that you're going to have 90 faces that you have to classify that are the non-marine area and the marine area. So you're going to have sandstone, coarse siltstone, fine siltstones, and all those other ones that you're going to be trying to classify. Those are the labels. Those are the names that are going to be showing in all the figures. And those are the adjacent faces. Those are the faces that the misclassification usually are going to happen more. So the sandstone also are going to have a lot of times that are going to be classified as the adjacent faces number 2. That's the coarse siltstone. And when you're going to plot our confusion matrix, you're going to see that most of the misclassification goes from these adjacent faces as well. So that's what you're going to be classifying. In here, I'm just going to run some metadata where I'm going to define what are the features initially. So those are the 5 well logs that we have: gamma ray, induction log, the density, and the photoelectric, and so on, and the 2 indicators, that are marine, non-marine indication. And also, what are well logs only? It's just the same as above, but with all those 2 indicators, because you're going to be doing a lot of transformations and feature engineering in these 5 features that we have here. I'm also defining in here what are the faces names, just for the plotting, and I'm defining some colors as well. When I'm going to be plotting, each one of those faces are going to have a different color, and I'm going to show you how it's done. I'm going to be separating what is target, and I'm separating what is going to be our test well by the end of the section. So you're not going to be training anything in this well, and you're just going to compare our classification. So I'm going to run this chunk. So I have this function from this utils.r that's plot well logs that are going to be plotting an example of this well log. So we're going to just run this chunk. And that's what we showed also in the presentation, in the PowerPoint. This is gonna be our test well. So we have the gamma ray, induction log, photoelectric, and those are the faces. So those are the colors that I was defining here in this hex color to be plotted in here. And also the name of the faces to be a shorter name to be presented here. That comes from these face names. Okay. So the first thing that I'm doing here, I'm gonna plot all the wells to make a small look, what's happening on each well, if they are okay, if you can find any problem. And in here, I'm just saving this legend information here, this object legend, to this variable, because we're gonna be using this later to do the per plot. It's just a trick for the GGLE to include legend in your per plots. So here I'm just running a for all the wells. And if you run this, we are gonna plot all the wells. So it's gonna take a couple seconds to do the plot. We have quite big data. Not so big, but we have a bunch of data. So those are all our, so we have the shrinkly, looks okay. If you come here to the Alexandria D, we can see that you don't have any information about the photoelectric. We didn't have this acquisition for this well. So those are where we're going to be using our data imputation. We're going to be using the other logs to recover the photoelectric effect. So we have this well chunko, that's going to be our testing. That's okay. This look GU is okay. These 15A also don't have the photoelectric, so we have two wells that has no photoelectric effect. This looks okay. This is no lines okay. This recruit F9 looks like to be a trouble well. I don't know exactly what's happening in here. And we have just one type of class defining it in here. So we don't know what's happening here. So what you're gonna do, you're just gonna be removing this well, because you're not sure if there is useful information or not in here. So that's the part of data cleaning. You're gonna be removing this well. And the other two wells, by the end, they are okay as well. So our first step is the data cleaning. So what I'm running here, I'm just selecting the well that the recruit F9s, all the rows that are recruit F9, they are not going to be entered in data clean. So all the wells that are not equal, that's the exclamation equal recruit F9, go to the data clean. So when you run this chunky here, Control Shift Enter, those are the wells that are remaining. We don't have the recruit F anymore. So that's the only cleaning that you're going to be doing in this data. So now let's just check it for missing data. I'm going to run this lapply, and I'm going to check and calculate the sum of the missing values for each one of the wells, for each one of the logs. So when I run this, we're going to note that we only have missing in the photoelectric. Any other well log or indicator has missing data. That's good. So we just needed to recover this. So our idea that you're going to be doing this, you're going to be running a regression model to recover. You're going to be using the other 4 logs, not going to be using these informations, these indicators. You're just going to be using these 4 logs to recover the photoelectric for these 2. So what I'm going to be doing here, I'm going to be creating, we had 9 wells in the beginning, 10 wells in the beginning, sorry, apologize. And we removed the recruit 9. So now we have 9 wells in the total. So what you're gonna do for the regression, you're gonna remove these 2 wells that are missing data from the, what I'm calling damaged wells. We're gonna be removing from the data. They are gonna be used for completing after, and also the test well. So what I'm doing here, I'm getting what are the good wells. Those are defining over there. So if you just run this one, Control Enter, those are all the wells that we had before. So we are going to be removing, oops. So the well name, oh, I forgot to do something. So the well name, I defined it up here in the metadata. Okay. So what you're going to be doing here now, you're going to be recalculating this well data. So this well data, well name, so alt dash, is going to be the unique of the data underscore clean, because we named it now the data as data clean. And $sign and the number, the name of the column, the well name. So when you run this in here, you're gonna get all the wells that are remaining. So those 9 wells. So you're gonna run this area in here. And then we have the damaged wells. Those are the D wells. So it's gonna be just an array that has Alexander D and Kizzy A. So we have the well names in here again. So the good wells are gonna be a difference between the D wells and also another one that's gonna be the test well. We're gonna separate another well to test our regression. So it's gonna be the same, it's gonna be Shanko that you're gonna be using. So this is a pipe. This is very useful in R because the output of this is gonna run in the pipe in here. So the output of well name is gonna be run, if you give a pipe, it's gonna be running the set difference of these 2. And then another pipe that's the output of this operation is gonna be run in here. So that's very similar to a pipe in Linux. So if you just run this selection, now our output in here, you're gonna see we removed the Alexander D and the Kizzy A. Another thing we want to remove for the good wells that you're gonna be using for the training, we want to remove the chunko. So you're gonna be removing as well the test well. So when you run that, our good wells are gonna be these. They're gonna be just 6 wells that are gonna be training our model. So I'm just gonna run this selection. So I created the good well. Here I'm separating for train and test. So the train are all the wells from the data clean that are in this array, good wells, and the test is gonna be the chunko. And here is how we're gonna be doing creating our regression model. Let me just fix this, our regression model to make predictions. So I'm just setting a seed in here, the random seed, to everybody keeps having the same output. So we have to so we're going to create a model named NNet fit. And what you're going to be doing from this is from the tidy models, we're going to be doing a multi-layer perceptron. So this is a neural network. And here you're going to decide some of the parameters that you want to use. You're going to be using a hidden unit. It's 40. That's going to be divided in how many layers, and inside the units of the layers you're going to have. The dropout, it's just a random number of the weights that are going to be dropped to avoid overfitting. And what are going to be the activation function for each one of these perceptions. That's how we do. We create this model, and then we have to set the mode that you want to do. You're going to be using for regression. You can be using also for classification. The next step, you're going to be setting the engine. So from each library you want to use. For this example, I'm using the NNet, but you can also use Keras if you want. Keras is going to take a little longer, and you have to change a little bit these parameters, but you can use Keras in here. To use Keras in here, you need to have a Python installation and the TensorFlow installed inside it, besides the package Keras that you have to install in R. It runs over the reticulate package. And here, after we create this model, in this selection, you are just creating a model. Okay, if you wanted to see what is this model, just run this selection. So I'm gonna just do, and then feed, and then I'm gonna create a pipe, translate. So this is from the parsnip, and then I can see what this model is presenting me. So those are all the configurations. So we have from the NNet, we have the max of iterations, the lineouts, all those informations. That's the one that we set from the tidy models. And this one is when it's converting to the library and NNet to run in the background. Okay, so I'm just gonna comment this row in here. It's Ctrl-Shift-C to comment. And to fit, we have to define a formula. So this formula is basic. What we want to be our target in function, that's this still in function of what? So in function of those features, that's going to be those 4 raw logs, and the data that you want to be training over. So if you just run this section, now it's going to take a few seconds, but it's done. So it's quite a fast model. If you try Keras, it's going to take longer to run. In here now, we have a trained model. You can even check how is this translate after the training. And, oh, okay. You cannot do that after training. I apologize for that. So now we can predict. So to predict, we're going to use our model and that fit, and then the new data that's going to be our test data that you define in here, our chunko. So if you just run in here, you're going to have our regression. So those are the values that you're going to be getting for our testing set. So I'm going to run just this. I'm going to save in this array pred for the regression. I'm just creating a new data frame with a melt for plotting in ggplot. So this is just a way to plot everything in one graph with different colors. So what I'm doing, I'm gonna be binding in columns the depth, the photoelectric, and the regression. So when I do that, I have this data frame with the depth, the photoelectric, and the predictions. So I just wanna compare if they're okay. So here, I'm gonna be converting as a table. That's a kind of data frame that it's more powerful in R. And then I'm gonna be renaming this column from .pred to predictions. So, oops. If we click here, so now it's named as predictions. And then I'm gonna be melting, and it's gonna be related to the depth. So you're gonna have just 2 columns after I melt. So it's gonna be like that. We have 3. So we have the depth, the variable that we have photoelectric, that was the column, the name of the column, and down there, if you look at the tail of these, if you look to the very end, we're gonna have the predictions as well. And those are the values that are the numbers. So we're gonna be doing that. It's very useful for the plots, because you're gonna be using a ggplot where you have to create the aesthetics. So our x is gonna be the depth, our y is gonna be the value that comes from these 2 plots. It's gonna be this one, the y, and the color are gonna be the variable. So that we call is this one. So this means that it's gonna be plotting 2 lines when you include this geom line, and you're just defining the color. So when you run this selection, that's what you're creating. You're creating this plot. So the red, the blue, the black is the true values of the photoelectric, and the red one are the predictions. We are getting a quite good prediction for this one. It's not perfect. If you had more data and probably more logs, we could get a closer result. But for data imputation for the wells that you have no information, that's going to be good. Now we're going to fill the missing data back to the data. So what I'm doing here, I'm just retraining the model now, including the test one, the chunko. So we're going to have more data. And then I'm going to predict in those two wells for those damaged wells in here. So that's what I'm be doing. Here, I'm just filling, I'm just including where it was empty. Now I'm including the predictions in here. And for this part, I'm just going to be plotting both of the wells and see they were empty before and how were the predictions after that. So from empty, now we have this information for the photoelectric. And here. We have to be really careful for this kind of techniques for data imputation, because if you don't have much information and depends the way that you're doing, you can include some bias in these, and this could not be a useful information by the modeling in the end. So the next step that you're going to be doing some data analysis, and they're going to be doing some pair plots. That's a pair that you're going to be plotting each one of those features with against each other, and they're going to be colored, the points, by the faces that we have. So this is one way to do. That's when you're doing R using the GG pairs from the GGL. So we can give you all those informations for it. And what I'm doing here, I'm just changing the colors of the points. I have to do one by one of each one of the small plots, each one of the faces inside there. So I'm just going to show what I'm doing. So first, I'm going to create these GG pairs. I created it in here. So if I just plot it in here, I should have this one popping out down here. So it might take just a second to plot. And they're going to see that the colors are going to have no effect in the legend. Remember that I saved the legend in the beginning of the code that I'm including in here. So yeah, so those are the default colors that we have for the ggplot and for the ggpair. So they make no sense. To change the colors in here, I have to do one by one of the faces. So if I do that, if I just run this part, I'm going to be changing the colors. And now I'm going to be printing it again. So again, it's going to take a few seconds. It takes a while to plot everything. So let's just wait. And the way I'm doing, I'm running for all the rows and then for all the columns. I'm including in this image PM in here. For each one of them, I'm changing the color fill manual and the color manual as well. And that's how we have now our pair plots with the colors that match the ones from the legend. So one observation that we got from looking in here are that they have the circular behaviors according to the faces, the type of these faces in here. An advantage to have this, not advantage, but the idea for the circular is that if you have a circular type of ways to divide stuff, if you want to create a boundary that you want to separate two circular events, it's going to have to be a classifier boundary that also have to be a circle to divide them. That's a very complex model to be created, and it can bring a lot of errors. So one way that you're going to be doing a way to go across this, you're going to be converting these pairs to do some polar coordinates. So everything that's circular in here, so both are gonna have the same circular, they're gonna have all the angles, but they're gonna have different radius. So what's gonna happen that in a polar coordinate, you're gonna have two lines, one for the different radius, and then you can just draw a straight line to divide them. So here I just wanted to show how to do this plotting from the Python library, from the reticulate. We have this function named import, where you can import any of the Python libraries inside here that you have installed in your environment. So I'm going to be importing the Seaborn as CNS, the Matplotlib as PLT, and the Pandas as PD. So here, I'm just going to be importing the library. In here, then, that I have imported the Seaborn, I can call the functions that are inside this. So it's very similar the way you're using in Python, but instead of a dot, you're going to be using a $sign. So it's going to be the Seaborn package, equivalent to the dot. That's going to be the $sign per plot. And then all the parameters, the way that you include for the per plots in Seaborn, in Python. The only thing that you have to think is that we have a data frame that are in R, so we have to convert to Python. So we just have to run this R to Py and our data frame. So here we are just plotting the data clean that are going to be using the well logs and the target. And the color are going to be the target, colored by target. So when you run this, you're going to be creating your plot. And to display, you have to do the PLT $sign show. So that's for the same way you do in Python. So it's going to take just a few seconds to create. And now you're going to be plotting in here. So just wait a few moments. And you're going to have an equivalent of the one that we did in R, but now in Python. And if you look, the Seaborn, it's actually required less coding and less information than what we did in R. So it might take a while. So I didn't play too much with this configuration. So you can see that it's cutting a little bit on the left, on the bottom, but it's just something that you need to change some configurations. I didn't spend much. I just want to show that a possibility. So we have the equivalent in here, there. Okay. So, okay, so let's go for the feature engineering now. So the next step that we need to do is by observing the circular events that it's kind of a little clear in this plot in here. We're gonna do the polar coordinate. So this is another function that came from this utils.r. So we're gonna be doing this Cartesian to polar in the wells. So this is the function that we are creating the data in polar coordinates. So we're going to be creating new columns. You're going to keep saving, keep the old ones, and you're going to include new ones that are going to be the polar coordinates of those. So if you run these, now that's what we have. We had all the columns as before, and also combining the two of those. For example, gamma ray is ILD, what's the radius and what's the angle in phi, in radians, and so on. And we're going to be doing that for combining all of them. So initially we had just a few columns, and now we have a total of 31 columns. So another thing that I'm going to be doing here that you're going to be using for our prediction is the formation. So formation we have here in numbers, in char characters. So I'm just going to be converting to a number, and I'm going to including this also as a feature that they're going to be using for the predictions. So we're going to just be converting this to a factor and then to a numeric. So when I'm doing that, now we have again all those same ones. And in the last column, now we have the formation that's going to be a double. So now it's being included as a number. in here for our predictions. So here, I'm just saving what are the features for the polar coordinates now that you're going to be using in the future. And another thing that you're going to be doing for the feature engineering is just computing the gradient of each one of those features, removing the formation. So just the gradient by depth. So that's another function that's inside the utils.r. So should be this one features gradient. So that's how we are doing. So now you're going to be computing the gradient for all of them and saving the new features for the gradient as well. So for these features, you're going to be using also the formation number, because we want to use all those features now to create a new feature that's going to be a clusters. I've read a lot of papers that says that your classification can be helped if you include some clusters in there. So I'm going to be using a k-means, and I'm going to be using all those columns as input, and I'm going to be calculating 9 centers. That means I'm going to be trying to find 9 clusters in the total, and then in the maximum of iterations. That's going to be doing that. So in here, I'm just going to be creating the, when I run this, I create an object named the cluster that has a bunch of information. If I run this, it has a bunch of information that you can find in here. Let me stop this because it was not nice. Let's look on the side here. So I have this clusters object. It's a list with 9 elements in it, and you have all this information. And what we want is this cluster in here. Those are actually the clusters that it calculated. So it would be this one. So it's going to be a lot of them. I'm just going to stop. So those are the clusters that are going to be calculated from these features. And then I'm going to include these as a new feature in here in the data grad. So now I have those final features for our classification that are going to be including also the cluster. And that's going to be all those features that we had here to all of those information. So now we have, oops, sorry. So now we have one more column that will be one more feature for our prediction, for our classification, that are the clusters. Okay, so now let's go for the gradient boosting. So initially we had 7 features to calculate our predictions, and now we have way more. So if you just calculate the length of the features, now we have 56 features to helping our prediction. So we started from 7 to 56. So included 49 more features there by doing all this work. And those help a lot for the classification. We did a report in this in 2018. I can even share the link, but that includes how changes the accuracy by just running the 7 features with no treatment to after you do that. We can include up to 10% points in our accuracy and our metrics. Okay. So what you're going to be doing here now for our classification, we need to convert those face columns from numeric to factor. That's a requirement for this package, XGBoosting in R. So it's going to be recognized as categorical column. You're going to be here separating what is the test and the training well now. So the test is going to be Shanko, and the train are going to be all the other 8 wells. In here, you're going to be creating a formula like we did before. You have to create a formula that is going to be the target in function of all the others. When we did the regression, it's quite easy to type this because you just have 4 features. So how we're going to be doing that with 56? I don't want to type all of them. So a trick is to use these paste commands where we can convert these vector features and you can collapse all the elements and separate them by just a plus sign. So we have these features. If you run this, we have a vector, right? If you run this paste 0 with this collapse in here, that's what is going to be created. It's going to be just one char object that has all this information. And then I'm going to do another paste that I'm going to be including the faces till in function and separated by nothing. I mean, when I include the separation, that has no space or anything. So now we have this large char object that is the faces in function of all the others, and to convert to a formula to be used there in the feed, we use as.formula, and we run this, you're going to have this formula. So we do this in just one line. And how we are going to be creating our model now. So this is our model, the gradient boosting. So again, from the tidy models, we're going to be using the boost tree. So we're going to have selected the number of trees that you're going to be using. I selected here 500. So it's going to be creating 500, one tree after the other. The depth of the tree, I selected to be 7. You can, after, change these and see if you can get better results. I did not work too much in this. I'm just showing how to do stuff. To stop iteration, if you don't have any improvement after 10 iterations, it's going to stop. So it's a hard stop. This mtry is just the random number of samples that you're going to be getting for each one of the leaves. So it's not going to get all the data. So it's going to be shuffling a little bit the data. That's good. And this is the learning rate for the minimization when you have one tree after the other. So that's the boosting tree. Then you're going to set the engine. That's going to be the XG boosting. You're going to be setting the mode to be classification. And you're going to be fitting on the train data set with that formula that you created up here. So if you just run this, it's going to take a few seconds, but it's going to run quite fast. You can even decrease the number of trees that you want to do. If you want to just do tests, you can try like 50, and then it's going to run way faster. In here, I'm just going to be calculating the predictions for the testing data set, and I'm going to be including as a new column predictions for the test. So it's going to be easier to do the plot later in here. So here, I'm creating this confusion matrix from the library ML matrix. So when you run this, we have to include here the predictions and the true values. You're gonna run these. That's the confusion matrix that are gonna be created. So those are absolute numbers. So that's how it was predicted. So we had 66 of these. Probably this is the sandstone that was predicted wrongly in here. What you're going to be doing here, I created this plot confusion matrix that's also in the utils.r that creates a better way to visualize this confusion matrix. So I'm just going to be including the row and the column names, and then I'm going to be doing the plot. And also I'm going to be including so we're going to be just plotting the confusion matrix in here. So we see that for a confusion matrix, to be a perfect prediction, we should have ones in the diagonal. So more diagonals be the full color and the rest be white, the best. So, but we had a lot of misclassification. This is the block that we have for non-marine data, and the misclassifications, they actually happen for the adjacent ones. So they have some similar response to the apparatus that can confuse our machine learning algorithm. So we're doing a very good job for this coarse siltstone, regular good job for this fine siltstone. And one that you have to take a look is this Mudstone. We actually predicted all wrong for Mudstone. You couldn't predict any correct. One of the reasons is because we don't have a lot of Mudstone examples in the data set. So it's a problem that we have imbalanced classification that I didn't work. I didn't take care with this, but we can. So we could not predict. We didn't have enough information to predict Mudstone. But all the others, they are not doing so bad. And here, just a few metrics, just for us to take a look. The accuracy and the F1 score. So for this proof of concept project, it's not bad. We have a 57% accuracy and a 0.39 F1 score. So we could improve this with doing more stuff, maybe more features, engineering, and more other stuff. And here, just to end, just the plot, the last plot with our predictions. So those are the true values, and those are the predictions. They are not bad if you look at this visually. So that would help a lot interpreter with his work. And you can see here, for example, this Mudstone is this dark blue. That is this one. It is classified for all of this area. So we could not find any Mudstone in here. But for all the others, they are not doing bad. Even the fine siltstone is being classified as the coarse siltstone that are the adjacent ones that are going to be creating more confusion in our machine learning model. But it's doing a good job, but there is a lot of room for improvement. So that's what I'd like to present for coding. So I'm just going to be doing some closing notes for today. This is the machine learning block for our learning labs. So we already presented the lab 4 that was natural language processing to classify severe injuries in the oil and gas industry. Today we presented this machine learning for lithology classification from wireline logs. And the next one, the lab 6, that's going to happen in 2 weeks from now, it's how we're going to be using deep learning, the package TensorFlow in Python. The next one is going to be in Python, the lab. We're going to be using TensorFlow to identify salt inside seismic sessions. So this is also another competition from the TGS that happened in 2018 in the Kaggle website. And you can download the data and try your solutions as well. But we're going to be present our solution, how we did it. Okay, so sorry, that's all that I had for today. If you have now any questions, please just type your question in here so I can see what you want to talk about. So I'm going to stop my sharing and the questioning time is open. So if you have any question, just go. So Ninoska has a couple questions. I might have missed, but for the 2 wells where P was missing, use the other good wells and predictions to fill the void of missing data. But aside from this, what other information did you use as control the prediction of the missing data? So for this one, I separated another well as a blind well. I separated the same well that I used the test for classification. I separated as well as a blind well for the regression part. So the second question we have here, do you know if all the wells are in the same basin or somehow in the same area? I'm not sure about that. I don't have the information, but I believe they are close to each other. So Paulina also made a question. How can we know if the clustering does not show the representative information since it was derived from the features, the repetitive information? Those are 2 different methodologies. Those are based on unsupervised learning. So it's going to be a little different. We are not minimizing any kind of error in this one. So we are just separating by similarity between data. It's a different approach than doing a classification, where you're doing a minimization when you know the answer. So, but if you have a little of repetitive information, that actually is going to help for the classification, but that's not going to happen 100% at all. So another question by Prince. Hi, did you try hyperparameter tuning and ranking scores? No, I didn't try tuning the parameters. I just did a proof of concept in this one. But again, the codes are going to be provided and you can download as soon as it's available from the Cruise website, and then you can try to do that. So Maddie, again, also made a question. What is your recommendation to compensate for missing lithologies or lithologies with small data? So there is a way to weight the classes before doing the classification. So you could work for balanced data. If you use the scikit-learn, for example, it has even an option there for using balanced data, imbalanced data, where you can balance by the weights. So the classes that appear less, they're going to receive a higher weight. So Prince, ask again, okay. So Pauline asked, are there any idea how to augmented the data set, create artificial wells? I think that's a very good question. That should be something really interesting to check. How to create artificial wells using some information. There are a lot of researchers trying to create wells from drilling information, from several other information that you have there. So that would be something interesting. But we need to create from some information that we have in this area. Maybe you can create from seismic, or maybe you can create from other information. Okay. So actually, our time for today is quite done. If you have any questions, I can answer, no problem. If not, I'm going to stop the meeting. So any other questions? Oh, I guess not. Okay, so if you don't have more questions, I'm going to be ending now. So I'm going to be stopping the record, and thank everybody for coming for today. It was a great participation from you guys, and I hope to meet you in 2 weeks from now. So have a nice day.